Before the invention of clocks, before the rhythmic ticking that now governs our lives, humanity looked upward. In the dance of light and shadow, in the patient arc of the sun across an endless sky, our ancestors found something profound. They discovered that time itself left marks upon the earth, that every passing moment could be read in the geometry of darkness cast by light. The sundial, perhaps the oldest scientific instrument known to civilization, was not merely a timekeeper. It was a window into the cosmos, a silent astronomer that revealed truths about our planet, our sun, and the intricate machinery of the heavens that would take millennia to fully understand. This is the story of shadows that taught us to measure the infinite, of stones and bronze that mapped the movements of celestial bodies, and of the brilliant minds across continents and centuries who learned to read the language of light. It is a tale that spans from the dusty plains of ancient Mesopotamia to the precision gardens of Chinese emperors, from the towering obelisks of Egypt to the mathematical elegance of Greek genius. In these simple instruments lies a history of human curiosity, ingenuity, and our eternal quest to understand our place beneath the turning stars. Long before the first sundial was crafted, before any human hand shaped stone to track the sun's journey, there was observation. Picture, if you will, a moment 30,000 years ago. A hunter stands at the mouth of a cave as dawn breaks across the landscape. Behind him, his shadow stretches long and dark into the shelter. As the sun climbs, the shadow shrinks, pulling inward like a living thing. By midday, it huddles small and dark at his feet. Then, as afternoon wanes, it reaches out again, stretching toward the east, growing longer with each passing hour until darkness swallows it completely. This daily transformation was impossible to ignore. Early humans whose survival depended on acute observation of their environment must have noticed that shadows moved with perfect consistency. The shadow at dawn always fell in the same direction. The shadow at midday was always shortest, and this pattern repeated itself with unwavering regularity, day after day, season after season. It was one of the first clocks nature provided, and it required no technology, no invention, only awareness. But shadows held deeper secrets. As the seasons turned, keen observers would have noticed something else. In summer, even the midday shadow was short, the sun climbing high overhead. In winter, shadows stretched longer, the sun never quite reaching the heights it achieved in warmer months. The shadow cast by the same rock, the same tree, the same standing stone, changed its length with the turning of the year. This realization was profound. It meant that the sun's path across the sky was not constant, but followed a grand pattern, a celestial rhythm that matched the cycle of seasons, the rhythm of planting and harvest, life and death. Archaeological evidence suggests that as far back as 5,000 years ago, perhaps even earlier, humans were deliberately using shadows for timekeeping. In ancient Egypt, workers used simple shadow sticks, pieces of wood or stone placed vertically in the ground, to divide their workday. These primitive instruments, called gnomons from the Greek word meaning one who knows, were the ancestors of every sundial that would follow. The gnomon cast its shadow, and the length and direction of that shadow told the story of the day's progression. But the Egyptians took this knowledge further. They recognized that the gnomon could do more than mark hours. It could mark the year itself. Around 3,500 years ago, Egyptian priests and astronomers began erecting obelisks, massive stone monuments that served both ceremonial and scientific purposes. These towering structures, reaching toward the heavens, were carefully oriented and positioned. Their shadows were observed with meticulous care, and through these observations, the Egyptians made a discovery that would prove fundamental to astronomy. They determined the length of the solar year with remarkable accuracy. By marking where the shadow of an obelisk fell at noon on the day when the sun reached its highest point in the sky, and then measuring the days until the shadow returned to that exact same spot, they calculated the year to be 365 days. This was accomplished not with complex instruments or mathematical formulas that would come later, but through patient observation and the simple geometry of light and shadow. The obelisk, standing silent and immovable, became a bridge between earth and cosmos, its shadow a finger pointing to celestial truths. The Egyptians also developed more portable timepieces. Shadow clocks dating to around 1,500 years before the Common Era have been discovered, sophisticated devices made of stone or wood. These were L-shaped instruments with a horizontal bar that cast a shadow onto a calibrated base. In the morning, the device was oriented toward the east, and as the sun rose, the shadow moved across markings that divided the morning into temporal hours. At noon, the device was reversed to face west, measuring the afternoon's progression. These shadow clocks represented a significant advancement, a deliberate engineering of time measurement that required understanding not just that shadows moved, but how they moved, and how that movement could be standardized and quantified. While the Egyptians pioneered early sundial technology, it was in ancient Greece that the science of sundials truly flourished. The Greeks approached the problem of timekeeping with their characteristic love of mathematics and geometry, transforming the sundial from a practical tool into an instrument of scientific precision. Around the 6th century before the Common Era, Greek astronomers began to understand something remarkable about the Earth itself. Through observations of sundials and celestial bodies, they reasoned that the Earth must be spherical. The evidence was written in shadows. When travelers moved north or south, they reported that the length of shadows at noon changed. A shadow that reached a certain length in Athens would be shorter in Alexandria to the south, or longer in Macedonia to the north. This could only make sense if the Earth's surface was curved, if the sun's rays struck different latitudes at different angles. Anaximander of Miletus, a philosopher and astronomer who lived around 600 years before the Common Era, is credited with introducing the gnomon to Greece and possibly inventing the first true sundial with a flat dial. He understood that the gnomon's shadow traced out curves rather than straight lines across a horizontal surface, and he began to map these curves with mathematical precision. This was revolutionary. It meant that sundials could be designed not by trial and error, but by calculation, by understanding the geometry of the sun's apparent motion across the celestial sphere. But the greatest leap came with the understanding of the analemma. Greek astronomers discovered that if you marked the position of the sun at the same time each day throughout the year, those marks would not form a simple pattern. Instead, they would trace out a figure-8 shape in the sky. This strange curve, the analemma, exists because of two factors: the Earth's axial tilt and the slightly elliptical shape of its orbit around the sun. The ancient Greeks did not know about elliptical orbits. That discovery lay 2,000 years in the future with Johannes Kepler, but they meticulously recorded the analemma's shape and incorporated it into their sundial designs. This knowledge allowed Greek craftsmen to create sundials of extraordinary sophistication. They developed hemispherical sundials, concave bowls with a gnomon rising from the center. The gnomon's shadow fell on carefully calculated lines etched into the bowl's inner surface, lines that marked not just hours, but also the changing position of the sun through the seasons. These instruments could tell both the time of day and the time of year simultaneously. Standing before such a sundial, an ancient Greek could read the date and the hour with a glance, all from the silent testimony of a shadow. One of the most famous Greek sundials was designed by Berosus, a Chaldean priest and astronomer who lived around 300 years before the Common Era. His design, a hemispherical sundial with the gnomon's tip positioned at the exact center of the sphere's curve, became widely popular throughout the Hellenistic world. The beauty of this design lay in its geometry. Because the gnomon's shadow always fell along curves that represented equal divisions of time, the hours could be marked with perfect regularity. This was a sundial that worked not just in one location, but could be calibrated for any latitude, a truly universal timekeeper. The Greeks also understood that different cities needed different sundials. A sundial designed for Athens at 38 degrees north latitude would not keep accurate time in Alexandria at 31 degrees north. The angle of the gnomon had to match the latitude of its location, pointing toward the celestial pole around which the stars appeared to rotate. This realization demonstrated a profound understanding of spherical geometry and the Earth's position in space. The ancient Greeks were not just building timepieces, they were encoding their knowledge of celestial mechanics into bronze and stone. When Rome rose to dominate the Mediterranean world, the Romans inherited Greek astronomical knowledge and engineering prowess, and they brought their characteristic practicality to sundial construction. For the Romans, sundials were not merely scientific curiosities, but essential tools of daily life, and they spread throughout the empire with remarkable speed. Roman sundials appeared everywhere, in public forums, in private villas, in military camps, and along the roads that connected the vast empire. The Romans mass-produced sundials with a precision that would not be matched until the industrial age. They created traveling sundials, portable instruments that could be adjusted for different latitudes, allowing merchants and military commanders to keep accurate time wherever their journeys took them. Some of these portable sundials were small enough to fit in the palm of a hand, marvels of miniature engineering with folding gnomons and latitude adjustment mechanisms. One particularly ingenious Roman design was the shepherd's dial, a cylindrical sundial that could be suspended from a cord. The gnomon was a horizontal pin that cast its shadow on the inside surface of the cylinder, where hour lines were carefully inscribed. By adjusting the position of the pin for different months, marked along the cylinder's length, the shepherd's dial remained accurate throughout the year. These instruments were practical enough for common use, yet sophisticated enough to incorporate seasonal corrections, a testament to how deeply astronomical knowledge had permeated Roman society. The Romans also built monumental sundials as displays of power and learning. In 10 years before the Common Era, the Emperor Augustus erected an enormous sundial in Rome's campus, Martius. Its gnomon was an Egyptian obelisk standing nearly 100 feet tall, brought from Heliopolis at tremendous expense. The obelisk's shadow fell across a vast pavement inlaid with bronze markers, creating a sundial of immense scale. This was not merely functional, but symbolic, a declaration that Rome commanded time itself, that the empire's reach extended even to the movements of the heavens. But the Romans discovered something troubling about sundials. When they conquered Greece and brought captured sundials back to Rome, they initially used them without modification. It took years before someone realized these sundials were keeping incorrect time. The problem was latitude. A sundial designed for Athens could not keep accurate time in Rome, which lay several degrees further north. The hours would be wrong, the seasonal markers misaligned. This realization led to a better understanding of how sundials worked and the importance of proper design for each location. Roman engineers also grappled with a more fundamental problem, one that reveals the limitations of solar timekeeping. The hours marked on a sundial are not equal to the hours we use today. Romans initially divided daylight into 12 equal parts, regardless of the season. This meant a summer hour, when daylight lasted longer, was actually longer than a winter hour. These were called temporal hours, and they created confusion in an empire that demanded precision for military campaigns, court sessions, and commercial transactions. Eventually, the Romans adopted equinoctial hours, hours of equal length based on the day of the equinox, when day and night are balanced. But this created a new challenge. Sundials now needed to be extraordinarily precise to measure these equal hours accurately throughout the changing seasons. As the Roman Empire declined and Europe entered a period of intellectual darkness, the torch of astronomical knowledge passed eastward. In the Islamic world, from the 8th to the 14th centuries of the Common Era, the study of sundials and astronomical instruments reached heights of sophistication that would not be surpassed for centuries. Islamic scholars had a powerful motivation for perfecting timekeeping: religious observance. Islam requires prayer at 5 specific times each day, times determined by the position of the sun. Additionally, Muslims must face Mecca when praying, a direction called the Qibla that varies depending on one's location. These religious requirements drove Islamic astronomers to develop extraordinarily precise methods for determining both time and direction, and the sundial became a central instrument in this quest. Islamic astronomers inherited and translated Greek scientific texts, but they did not simply preserve this knowledge. They advanced it dramatically. They developed mathematical techniques for calculating sundial designs for any latitude and for any orientation, not just horizontal dials. They created vertical sundials, sundials mounted on walls facing different directions, each requiring complex mathematical transformations to account for the wall's orientation relative to the sun's path. One of the most brilliant minds of this era was Abu Rayhan al-Biruni, a polymath who lived around 1,000 years ago. Al-Biruni wrote extensively on sundial construction, describing dozens of different types and presenting the mathematical formulas needed to design them. His work demonstrated a deep understanding of spherical trigonometry, a branch of mathematics essential for calculating how shadows would fall on surfaces of any shape and orientation. Al-Biruni's texts were comprehensive treatises that covered not just practical construction, but also the theoretical underpinnings of solar timekeeping, making connections between sundials and broader astronomical phenomena. Islamic craftsmen created sundials of breathtaking beauty. Many were made of brass, intricately engraved with mathematical lines, and decorated with calligraphic verses from the Quran. These were scientific instruments as works of art, objects that merged utility with aesthetic perfection. Some included compass roses to determine the Qibla direction, combining timekeeping with spatial orientation in a single device. The astrolabe, perhaps the most sophisticated astronomical instrument of the medieval period, was perfected in the Islamic world. While not strictly a sundial, the astrolabe incorporated sundial principles and could be used for solar timekeeping, along with a host of other astronomical calculations. It was a mechanical model of the heavens, capable of solving problems in astronomy, astrology, timekeeping, and surveying. The astrolabe represented the culmination of centuries of astronomical knowledge, compressed into a handheld device that a skilled operator could use to compute the movements of celestial bodies. Islamic astronomers also made crucial discoveries about the equation of time, the difference between solar time as measured by a sundial and mean solar time measured by a mechanical clock. They recognized that a sundial does not keep perfectly regular time throughout the year because Earth's orbit is slightly elliptical and its axis is tilted. At certain times of year, a sundial might run as much as 16 minutes fast or slow compared to mean time. Islamic astronomers created tables showing these variations, allowing sundial readings to be corrected for perfect accuracy. This was a profound insight, revealing that even the sun, the most reliable timekeeper available to ancient peoples, followed a rhythm that required mathematical correction to achieve perfect regularity. While sundials were being perfected in the Mediterranean and Middle Eastern worlds, parallel developments were occurring in China and the broader East Asian sphere. Chinese astronomers had been observing shadows and using them for timekeeping and astronomical calculations for thousands of years, developing their own unique approaches to solar observation. As early as 1,100 years before the Common Era, Chinese astronomers were using gnomons to measure the sun's position. But they were interested in more than just telling time. Chinese scholars recognized that careful measurement of shadow lengths could reveal fundamental truths about the cosmos and the Earth itself. During the Han Dynasty, around 2,000 years ago, Chinese astronomers built remarkably tall gnomons, some reaching heights of 40 feet or more, to measure shadows with extreme precision. These measurements served a cosmological purpose. In Chinese thought, the emperor ruled with the mandate of heaven, and astronomical observations were seen as a way to maintain harmony between heaven and earth. Accurate astronomical knowledge was therefore essential to legitimate governance. Imperial astronomers maintained careful records of shadow measurements, solar and lunar positions, and astronomical phenomena, treating this knowledge as a state secret of tremendous importance. Chinese sundials took various forms. Some were horizontal dials similar to those in the West, but others were unique to Chinese astronomical tradition. The equatorial sundial, with a gnomon parallel to Earth's axis and a dial in the plane of the celestial equator, was perfected in China and demonstrated a sophisticated understanding of celestial coordinates. This design had the advantage that the hours could be marked at perfectly equal intervals around the dial, a significant simplification compared to the complex hour curves required on horizontal sundials. One of China's greatest contributions to the science of shadow measurement came during the Yuan dynasty in the 13th century. Guo Shoujing, a brilliant astronomer and engineer, constructed an enormous gnomon tower at Yangcheng, designed for extreme precision in measuring the sun's shadow. This structure, still standing today, was part of a network of astronomical observations conducted across China to improve the accuracy of the calendar. Guo Shoujing used these shadow measurements to calculate the length of the solar year to within 26 seconds of the true value, an achievement of stunning accuracy for the 13th century. Chinese astronomers also grappled with the equation of time, independently discovering the variations in solar timekeeping. They created sophisticated water clocks that kept mean time and used these in conjunction with sundials to map out the equation of time with precision. This dual approach, combining solar observation with mechanical timekeeping, represented an advanced understanding of the complexities inherent in measuring time. In Japan, Korea, and other regions influenced by Chinese culture, sundials and shadow measurements followed similar patterns, adapted to local latitudes, and incorporated into local astronomical traditions. The transmission of knowledge across Asia created a rich tapestry of timekeeping methods, each culture bringing its own innovations to the ancient art of reading shadows. What made sundials so remarkable, what elevated them beyond mere timekeepers to true scientific instruments, was their ability to reveal hidden truths about the cosmos. Every sundial, properly understood, was a device for astronomical discovery. The secrets they held would take humanity thousands of years to fully comprehend. The most fundamental revelation written into every sundial was the Earth's rotation. The shadow of a gnomon sweeps across its dial, not because the sun moves, but because the Earth turns beneath the sun. Ancient observers did not understand this. They believed the sun traveled across a fixed Earth, rising in the east and setting in the west through its own motion. Yet the sundial's operation was actually demonstrating the Earth's rotation, a truth that would not be widely accepted until the 16th century, when Copernicus proposed his heliocentric model. But sundials revealed something even more subtle about Earth's motion. The angle at which a gnomon must be set to keep accurate time is equal to the latitude where the sundial stands. This gnomon must point toward the celestial pole, the point in the sky around which the stars appear to rotate. This requirement emerges naturally from the geometry of Earth as a rotating sphere. Ancient astronomers, without knowing they lived on a globe, had discovered through sundial design that something about their location on Earth's surface affected how shadows fell. They were measuring latitude before they fully understood what latitude meant in terms of a spherical Earth. The changing length of the noon shadow throughout the year was another cosmic secret written in light and darkness. This variation occurs because Earth's axis is tilted 23.5 degrees relative to its orbital plane around the Sun. In summer, for observers in the northern hemisphere, Earth's north pole leans toward the Sun, bringing the Sun higher in the sky and creating shorter noon shadows. In winter, the North Pole tilts away, the Sun stays lower, and shadows stretch longer. Ancient astronomers who carefully measured these shadow lengths throughout the year were actually measuring Earth's axial tilt, though they conceived of it as the changing height of the Sun's path across the celestial sphere. The equation of time, that variation between sundial time and mean time, encoded information about Earth's orbital mechanics. The fact that sundials run fast or slow at different times of year is partly due to Earth's elliptical orbit. When Earth is closer to the Sun, it moves faster in its orbit, and when farther away, it moves slower. This variation in orbital speed causes slight variations in the apparent motion of the Sun across the sky. Ancient astronomers who mapped these variations were actually measuring the eccentricity of Earth's orbit, though they lacked the conceptual framework to understand what they were observing. Sundials also contributed to solving one of the most challenging problems in history: determining longitude. While latitude could be found relatively easily by measuring the height of the sun or stars, longitude required accurate timekeeping. A difference of 1 hour in time corresponds to 15 degrees of longitude. If a traveler could carry accurate time from their home port and compare it to local solar time at their destination, they could calculate their east-west position. This is why the development of accurate marine chronometers in the 18th century was such a breakthrough. But for thousands of years, sundials represented humanity's most reliable timekeepers, and their principles informed the eventual solution to the longitude problem. As understanding of sundials deepened, they began to appear not just as portable instruments, but as permanent architectural features incorporated into the very buildings of civilization. Churches, mosques, palaces, and universities featured sundials on their walls and in their courtyards, transforming structures into instruments for measuring the cosmos. These architectural sundials took many forms. Vertical sundials adorned south-facing walls throughout Europe and the Mediterranean, their gnomons casting shadows across hour lines that compensated for the wall's vertical orientation. Some churches featured meridian lines, carefully aligned north-south lines on the floor, where light from the sun at noon would fall through a small hole in the roof. These meridian lines served both astronomical and ecclesiastical purposes, helping to determine the date of Easter, which depends on complex astronomical calculations involving the spring equinox and the cycles of the moon. One of the most famous architectural sundials is the Cathedral of Santa Maria del Fiore in Florence, Italy. In 1465, the astronomer Paolo dal Pozzo Toscanelli installed a gnomon in the cathedral's dome, nearly 300 feet above the floor. At noon, sunlight passing through a small hole in the dome cast a spot of light on the cathedral floor, marking a meridian line that stretched across the marble. This enormous sundial was used for astronomical observations for centuries, helping to refine the calendar and study the sun's movements with remarkable precision. Such monumental sundials represented the intersection of science, architecture, and theology. They were physical embodiments of humanity's desire to align earthly structures with celestial order, to make buildings that participated in the grand machinery of the cosmos. Standing in a cathedral where a sundial traced the sun's path across sacred space, the boundary between the terrestrial and the divine seemed to dissolve. Time, measured by these instruments, became a bridge between the human and the eternal. Garden sundials became popular in the Renaissance and later periods, serving both practical and aesthetic purposes. These were often elaborate constructions, with gnomons shaped as mythological figures or decorated with mottos about the passage of time. Some featured multiple dials on different faces, oriented to tell time from various viewing angles, or included lunar dials that could indicate time by moonlight on clear nights. These garden sundials were conversations in stone and metal about mortality, eternity, and the rhythms that govern existence. The inscriptions on sundials often reflected philosophical meditations on time. Latin phrases like umbra sumus, we are shadows, or horas non numero nisi serenas, I count only the sunny hours, appeared frequently, reminding viewers that the sundial was more than a tool. It was a symbol of time's passage, of light and darkness, of the measured progression of mortal life. The sundial's dominance as a timekeeper began to wane with the development of mechanical clocks in medieval Europe. By the 14th century, large mechanical clocks were being installed in church towers and town squares, keeping time through the regulated motion of gears and weights rather than the sun's shadow. These mechanical timepieces had a crucial advantage. They kept mean time, running at a constant rate regardless of season or weather. Initially, mechanical clocks were set using sundials. The sundial was still considered the true timekeeper, and clocks were merely convenient devices that approximated solar time. But gradually, this relationship reversed. As clockmaking improved, becoming ever more precise and reliable, sundials began to be checked against clocks rather than the other way around. By the 18th century, with the development of pendulum clocks and later chronometers, mechanical timekeeping had surpassed solar timekeeping in both accuracy and convenience. Yet sundials did not disappear. They remained popular as decorative objects, as symbols of traditional wisdom, and as educational tools for teaching astronomy and the geometry of timekeeping. Even today, sundials grace gardens, parks, and public squares throughout the world, silent reminders of humanity's first attempts to measure and quantify the passage of time. The principles discovered through sundials continue to matter. Modern satellite navigation systems like GPS must account for the equation of time and Earth's complex motions, the same phenomena that made sundial design challenging thousands of years ago. Solar architecture, designing buildings to maximize useful sunlight and minimize energy consumption, relies on understanding how the sun's position changes throughout the day and year. Knowledge first quantified through careful observation of sundial shadows. In recent decades, there has been renewed interest in sundials as precision instruments. Enthusiasts and scholars have built highly accurate sundials incorporating corrections for the equation of time, allowing them to keep time as accurately as many watches. These modern sundials represent a full circle, a return to solar timekeeping, but now armed with complete understanding of the astronomical principles that make such instruments work. Stand before a sundial on a clear day and watch its shadow move. In that simple observation, you are witnessing the same phenomenon that captivated humanity for thousands of years. The gnomon points toward the celestial pole, aligned with Earth's axis of rotation. The shadow sweeps across the dial, not through any motion of its own, but because you, the sundial, and everything on Earth's surface are rotating together beneath the sun. The shadow's position encodes your latitude, the date, the time, the equation of time, the obliquity of Earth's axis, and the eccentricity of Earth's orbit. All of this information has been there all along, written in the language of light and darkness, waiting for eyes capable of reading it. The story of sundials is ultimately a story about human curiosity and ingenuity. Our ancestors looked at shadows and saw not just darkness, but information. They recognized patterns in something as ephemeral as the play of light across ground, and they learned to read those patterns with increasing sophistication. From simple sticks in the ground to elaborate hemispherical bowls, from portable brass instruments to architectural installations in cathedrals, the sundial evolved as human understanding deepened. What makes this story remarkable is that it happened independently across multiple civilizations. Egyptian priests, Greek philosophers, Roman engineers, Islamic scholars, Chinese astronomers, all looked up at the same sun, observed the same shadows, and arrived at similar conclusions. They all discovered that shadows could measure time and reveal truths about the cosmos. This parallel development testifies to something fundamental about human nature. We are creatures who seek patterns, who find meaning in observation, who build tools to extend our senses and amplify our understanding. The sundial taught humanity to think in terms of geometry and mathematics, to see the world as something that could be measured and calculated. It required understanding three-dimensional space, spherical geometry, and the regular motions of celestial bodies. These cognitive tools, developed partly through the study of sundials, would prove essential for all subsequent scientific advancement. The sundial was not just a timekeeper. It was a teacher, an instrument that educated civilization about the cosmos and about the power of careful observation and mathematical reasoning. Today, we live in a world where atomic clocks measure time with precision beyond anything ancient astronomers could have imagined, where every smartphone knows the exact time adjusted for local time zones and daylight saving. We have seemingly transcended the sundial, moved beyond the need to look to the sky to know what hour it is. Yet, the fundamental truth remains. We still live on a rotating planet, orbiting a star, and the rhythm of day and night, season and year, still governs our lives in profound ways. The next time you see a sundial, perhaps in a garden or a park, take a moment to consider what it represents. It is not merely a quaint antique or a decorative ornament. It is a link to thousands of years of human effort to understand time and the cosmos. It is a reminder that simple observations, patiently recorded and carefully considered, can reveal profound truths. It is evidence that the universe is knowable, that the patterns governing existence can be comprehended through reason and mathematics. The shadow cast by a sundial's gnomon is more than just absence of light. It is a messenger from the sun, carrying information across millions of miles of space, information about distance and angle, rotation and revolution, the architecture of the solar system itself. For thousands of years, humans learned to read that message with increasing clarity, and in doing so, we learned to read the book of nature itself. The story of sundials is far from over. As long as the sun shines and objects cast shadows, these ancient instruments will continue to work, silent and faithful, marking the hours with the same precision that captured the imagination of our distant ancestors. They stand as monuments to human curiosity, testaments to the power of observation, and reminders that sometimes the deepest truths are written not in books or tablets, but in the dance of light and shadow across the face of the earth. Subscribe to uncover more whispers from the past, where history and science merge into stories that transcend time itself.